This is the screencast for section 2.1, example 2, finding an instantaneous speed. So in example 1, we talked about two different cars traveling, one at various rates but having an average speed of 60 miles an hour, and then another one traveling exactly 60 miles an hour at the same time. Well, now let's look at that car that travels a little bit more than 60 and a little bit under 60, but still has an average speed of 60 miles an hour. Let's find its instantaneous speed at a certain spot. So we looked at a rock in example 1 that was falling off of a cliff. And we want to find the speed of the rock in example 1 at the instant t equals 2 seconds. So not over the first 2 seconds, but at the instant 2 seconds. So in my first attempt, I'm going to use the same point to create a slope at an instant. So like in example 1, we said if it was over the first 2 seconds that we started at 0 and ended at 2. This one, if we're going to find the slope at 2 seconds, the beginning and end of 2 seconds is at exactly the same spot, 2 seconds. So I would use my first point 2, 64 and my second point 2, 64, and if I find the slope, I get 0 over 0. Which is undefined, so that doesn't really help me find an instantaneous rate of change. It helps me with an average rate of change, but not instantaneous. Well, my second attempt is I'm going to make a second point really close to 2, 64. So 2.00001, 64.00064 then. So I plugged in 2.00001 into my y equals 16t squared from example 1. Well, then I get a little tiny amount in the top, 0.00064, all over 0.00001, and I get about 64.00016 feet per second, which is approximate, but it is not exact, because that's actually an average rate of change over a 1/100,000th of a second. I want instantaneous. So in my third attempt, here's what I'm going to do from here on out. I'm going to say h is an unknown teeny tiny amount, getting really close to 0 to create a second point. So h, we don't even know how small h is, but it is infinitely small. Yeah, infinitely small, sure. So now the 2 points that I'm working with are 2, f of 2, so 16 times 2 squared, which we did find out was 2, 64. And then the other one will be 2 and a little bit, so a teeny tiny amount away, infinitely small. So not 0.00001, but even smaller than that, like really small, keeps getting smaller. And then that would be, the y value there would be 16 times 2 plus h squared, which I don't know how much that is. So I'm going to find the average rate of change between these 2 points. So my y2 is 16 times 2 plus h squared, and then minus my y1 is 16 times 2 squared, which I know is 64, but I'm going to write it out this way for now. Then my x2 is 2 plus h, and my x1 is 2. Well, let's see. I'm going to expand out the 2 plus h squared, so I get 16 times 4 plus 4h plus h squared, and then there's my minus 64. All over, let's see, 2 plus h and then minus 2 is just going to be h. Now I'm going to distribute my 16, so I get 64 plus 64h plus 16h squared minus 64 all over h. And as you can see, the 64 in front and the minus 64 in the back will cancel, and that should happen always. So now I'm going to start to simplify even more. 64h plus 16h squared all over h. I can simplify by canceling out an h in each one of those. So 64 plus 16h. Now remember, the idea behind h is that it should go really small. So let's take the limit as h approaches 0. of 64 plus 16h. Let's make h get really, really, really small. Well, if h approaches 0, as h gets to 0, that's actually going to equal 0. So 64 plus 0 is 64 feet per second. So as you can see, the estimate I made in my second attempt was really, really close, just not exact. This one is going to be exact. We created a little tiny point, very, very, very close, and took the limit as that the distance between the 2 points approaches 0. So the one x value is 2, the other x value is 2 plus something getting very, very small approaching 0. And we get 64 feet per second. Now the now try problem asks us to find the speed of the object at t equals 3 seconds to confirm our answer algebraically. So at, if you remember from example 1, the average speed over the first 3 seconds was 48 feet per second. And as we said, since the rock started at a velocity or a speed of 0 feet per second, it's got to be going way faster than that after towards the end to have an average of 48 feet per second. So I'm going to estimate it's going to go way faster than 48 feet per second, but let's find out. I'm going to use the point 3 comma 16 times 3 squared, and then a point a teeny tiny amount away from that. 3 and a little bit is going to be our x value, which means our y value is going to be 16 times 3 plus a little bit squared. I want the distance away from these two x values to approach 0. So I want h to get really, really, really small, almost to 0. So I'll look at, let's see, y2 minus y1 over x2 minus x1. I'll expand out and then simplify my rational expression. As you can see, my 144's cancel out because I have a positive 144 in the front and a negative 144 in the back, which is just like we said it was going to happen. Now I can't plug in 0 for h yet because that would be 0 over 0. So I have to simplify out an h first. And now that that h has been simplified out, if I plug in 0 for h this time, I won't get 0 over 0. I'll get 96 plus 16 times 0, which is 96 feet per second. Which we said it was going to be much faster than the average speed over the first 3 seconds of 48 feet per second.